Hello and welcome to my video tutorial on linear models in R. We will talk mostly about various types of regression models, and we'll start with the simple linear regression. Overall, regression models, they are the workhorse of statistical analysis, especially the linear type of regression model. It can be used for answering all kinds of research questions. More specifically, regression models can be used for predicting one variable, the so-called dependent variable based on independent variables. So even in some modern machine learning applications, the statistical techniques that are used at the foundation are often regression models, where computers learn from data and capture that knowledge in the form of a regression model. So it's a very powerful statistical technique. It was developed almost 200 years ago by Francis Galton, who was a British or English scientist and polymath who has made contributions in all kinds of areas, in all kinds of sciences. Specifically, he's quite famous for his analysis of genetic data on fathers and sons. So he came up with this terminology like regression towards the mean by analyzing the height of fathers and parents and their children. And as a part of that exploration of how parents' genetics, or I think at that time genetics was not a science, it was not something that was discussed explicitly, but he was basically interested in the question of how parents' characteristics influence characteristics of their children. And then later on, this research agenda was led to the discovery of genetics, where scientists claim that the kind of genes that your parents pass to you are largely determinantial to the way you are, to your physical and also psychological characteristics. So as you can see, this model was developed almost 200 years ago, but it's still around. It's still being used in all kinds of applications. So over the years, all kinds of techniques derived from regression have been developed. For example, generalized linear models, regression trees, penalized regression, and many others. They all share similarities with regression modeling, and typically all those techniques, they fall under the umbrella of linear models. Jumping forward a little bit, the reason we're saying linear models is that a line, just like this one, is used to approximate a relationship between two or more variables. So that's what it is. Okay, let's start with the simplest form of regression analysis. It's called simple linear regression. It's called simple because we're dealing with only two variables, x and y. So what you're trying to do, you're trying to predict the so-called dependent variable, or dvy, based on the so-called independent variable, or ivx. Okay. When you're predicting, you're also showing that these two variables are related. So if x can be used to predict y, it means that x and y are related. They somehow work or interact together. So that's why we call it simple, because we're only talking about two variables, the relationship between two variables. Now, the reason y is called dependent is that the way you model the relationship, you're saying that somehow y depends on x. Now, x is independent because it doesn't depend on anything. In fact, it's used to predict y, right? So that's why it's called independent. So independent variable is also the predictor, while y is the variable of interest. That's something that we're trying to predict. So that's why we call it simple, because again, we're dealing with only two variables, an independent variable and dependent variable. Now, why is it linear? Well, because we're trying to describe the relationship between x and y with a line. And here, at least the first part, it looks exactly like an algebraic expression for a line, for a straight line. I'll leave that e part out for now. So I'll just talk about this part. Probably in high school you took algebra, or in college you had to take algebra, and this is where you discussed this general equation, algebraic equation for a straight line. So this is how a straight line is described in the so-called Descartes system of coordinates, or XY system of coordinates. It's described using the following equation: y equals ax plus b. And letters, of course, letters can be different. It doesn't matter which specific letters we use to describe this relationship. So this green line is described by the following equation: y equals 2x plus 1. Okay, so a in front of the x, we're talking about this coefficient. So a in front of the x equals to 2, while b, the so-called intercept term, equals to 1. Okay, so this is what intercept term means. We're talking about 1 here. It means that the line intercepts y-axis at 1, right? So that's exactly what you see here. This green line intercepts y-axis at point 1. Okay. Now, what does a coefficient a, or number 2 in front of x, represent? Well, it represents unit change in y related to 1 unit change in x. The best interpretation of the slope, this is this is intercept. This is the so-called slope of the line. So the best interpretation. Well, actually, there are two good interpretations of the slope coefficient in front of x. One is like just a visual, simple interpretation. It means that how steep your line is. So y is kind of steep, right? It's going up very rapidly. Okay. So the more the slope coefficient, the steeper the line, right? So here we have 2, which is quite steep. Okay. So this means that when x increases by 1, y increases by 2, because that's what the slope coefficient represents. So for example, here, let's say we start with this point. X increases from 0 to 1, so it increases by 1 unit. But y, the value of on the y-axis increases from 1 to 3, which means it increases twofold, right? So this is what this coefficient represents. Based on the line, what is the change in y for 1 unit change of x? So this line is very steep. Now this line, y equals 0.5 x minus 1 is this equation in blue is represented by this blue line, right? Now minus 1 is the intercept term, which means that this blue line intercepts the y-axis at minus 1, and that's exactly where you see it intercepting. This blue line is intercepting y-axis at the point minus 1. Again, 0.5 is the slope coefficient, the so-called a coefficient in front of x. It shows by how much y will change when x changes by 1 unit. So here, when x changes by 1, so let's say x changes from 0 to 1, y changes from minus 1 to minus 0.5, which means it changes only by 0.5. Okay. Now these interpretations also bring us to the mathematical definition of the slope coefficient. It's rise over run, right? So rise delta y, change in y, divided by delta x, change in x. Okay, so that's the mathematical equation. So for example, for this line, if you want to compute the slope of this blue line, you need to divide rise over run. So the run, let's say for this interval, is from 2 to 4, which is 2. So the run is 2, the rise is 1, right? Because y has increased from 0 to 1 over this run, okay? So if you divide 1 by 2, you get 0.5, and that's exactly what this coefficient is, okay? So once again, this equation right here, y equals ax, is y equals ax plus b, is used to describe a relationship between two variables, y and x, using a straight line. Now you may be wondering, like, what's that e term all about? Like, why we're adding an e term? Well, this is how it works in practice. You see here we have a bunch of dots that represent the relationships between father's height in inches and son's height. So each father has a son, and that observation for father-son pairs is plotted here using the scatter plot. Okay, so that's what you're trying to do. You're trying to build a line that approximates the relationship between father's height in inches and son's height in inches. So you have two variables here. Okay, son's is the y, it's the dependent variable. Son's height in inches is y, the dependent variable. Father's height in inches is x, the independent variable, right? So you're trying to predict the dependent variable, son's height in inches, based on the independent variable, which is father's height in inches. So you see those points in the scatter plot, they represent actual observations. So we're trying to find a line that minimizes the distances between all these points. Okay, so in other words, when you look at those observations, it doesn't look like a line, it's more like a sausage, right? So line is a very rough approximation of how this relationship really looks like. Okay, because this line is a very rough approximation, it's more like a cloud, right? Like a stretched cloud or a sausage, something like that. Because line is a very rough, very dry mathematical approximation of the relationship between fathers and sons. So for example, here you're using this line to predict, let's say, you build this regression line and you're using to predict the height of a son, of a father who is 70 inches tall, something like that, right? I think it's in inches. I may be wrong. Yeah, I think it's in inches. So you see the line says if a father has a height of 70 inches, the height of son is also 70 inches. But in reality, of course, look, for every father that has a height of approximately 70 inches, you have a son who is 62 inches. You have, somebody, a father who is 70 inches high has a son who is almost 80 inches, right? So there is that spread, okay? There's that spread. So the regression line never captures the actual relationship between x and y. So that's why you add error term, okay? So errors are all those deviations of points from the actual line. So that's what this error term represents. But again, as you can see, most of the points here for fathers who are 70, they're close to 70, right? And by the way, this is the phenomenon of regression this is something related to the phenomena of regression towards the mean, which means that things tend to be like average, right? Things tend to be average. In other words, what Galton has discovered, he discovered that very tall fathers tend to have, on average, tend to have sons that are average, and very short fathers or parents, they tend to have sons that are not very short but also average. So most points are clustered around the average value, something like that, right? So that's why we have E added, because this line is never a perfect representation of the relationship between X and Y, okay? So let's start building a very simple regression model using the father-son dataset by Francis Galton. So that was, I think, the actual dataset that Galton used 200 years ago to do regression analysis and to discover what seems to be like an early attempt to investigate the concept of genetics. And this is something that has also led to this discovery of the phenomena regression towards the mean. So for that demonstration, we'll install a package called using R, and then we will also activate the ggplot2 package and also look at what the fathers and son dataset contains, which is a part of using R, I believe. So we'll run this expression, this code right here. Okay. And here you see the head of the dataset, which means the first 6 observations. So you have father's height in inches and son's height in inches. So that's what each observation represents. So let's visualize how a regression line looks like. So for now, we're just using a linear method, which is very similar, if not identical, to the regression. I forgot what it's identical. I think it is. So what it will do, it will build a regression line, but it will not give you any output. It will just visualize a line based on the regression method that approximates the relationship between father's height in inches and son's height in inches. So we run it, and that's the same visualization that I showed you before, right? So you have a line that approximates the relationship between father's height and son's height. This line is not a perfect representation of the relationship, more of an approximation. So now we'll build a formal regression model. In R, to build a formal regression model, to build a linear regression model, you use the LM function. So this object heights LM will contain the output of the regression model. So we'll run the regression model, and then we'll just display the content of this object. So here we got our coefficients. We see that the intercept, meaning B term, we're talking about this intercept, is 33.89 approximately. and then the coefficient in front of father's height, which is our x, which means the slope of the line that represents the relationship between son's height and father's height, is 0.5. Okay, so the line, it has the following steepness because the coefficient is 0.5, but the intercept term is like way up there. It's at 33 approximately. Okay, so we build this line using the LM method. Okay, now to see the details related to the model, because it's a very basic output, you just get, it's just the LM function, the object spits out two coefficients. Use the summary function. So the summary function is applied to the object height LM that stores the output of the regression model that we created right here. So if you run the summary, you will see a detailed output, and this is what most researchers want to see. They want to see this detailed output. And within this detailed output, there are a few very important indicators that everybody is paying attention to. Okay, number one, let's start with this. We are looking at how good the overall regression model is. Okay, now one statistic that's worth starting with, although it's not it's not that frequently discussed, is F statistic. So F statistics is very high. It's 361, so the p-value is close to 0. So this is the number using a very small decimal number close to 0 using the scientific notation. So basically, what this low p-value, which means almost close to 0, shows you the chance that this regression model is a result of some kind of randomness and not the true relationship between x and y is almost 0, right? So to reverse that, to phrase it in a reverse way, what this F statistic shows is that we're almost 100%, it's never 100%, but we're almost 100% certain that our regression line, right, is the valid representation of the true relationship between father's height and son's height in the population, right? Now, why I'm saying the population? Well, look, we're not analyzing the relationship between height of fathers and sons for all fathers and sons in the world, right? We're trying to generalize to that population, meaning to all fathers and sons, but we only have a sample of data, right? So that's why we need to have this statistic to see how good the overall model is. Another important output of regression model is the so-called R-squared or adjusted R-squared. They're almost the same. The only difference is that adjusted R-squared penalizes somebody for adding additional predictors, meaning independent variables, into the model, because there's that idea that if you keep adding predictors, your R squared will go up, and for that since your model needs to be parsimonious, you need to be penalized for that. There's also that phenomena of overfitting, where by adding predictors you will increase your R squared artificially, which means that it's not that you're improving your ability to predict things in the real world, you're just fitting things on the data better, right? So what does R squared represent? Well, either R squared or adjusted R squared, they have the same interpretation approximately. R squared means what percent of variation in Y, which is the height of sons, is explained by the independent variable x. So in our case, it's 0.25 or 25%. So it means that only 25% of variation in son's height is explained by father's height. Okay. Now you may be wondering, what about the remaining 75%? Well, 75% is unexplained, right? So something like that. Look at this slide. On average, you see, so here we're looking at the relationship between specific observations for fathers and height. So for example, for this particular observation right here, talking about this dot, you explain the line explains some, approximately 75%, but not all variation. So on average, we're saying we're only explaining 25% of variation. Okay. Now the remaining 75% is all kinds of other factors that determine height of a particular son. Maybe this is his or her mother's height. Maybe it's nutrition. Maybe it's the month where the person was born. So a lot of things, more specifically 75% of variation in Y is unexplained. So only 25% is explained by our model. Now, is it good to have 25% explained by your model? Well, in social sciences, it's okay. I mean, it's something that requires like human interpretation. I would say that in social sciences, anything above 20 or 30% is considered to be good, because in social sciences we're dealing with very complex phenomena where, so right now we're investigating sun's height, which is our phenomenon of interest. Typically, social phenomena, by social phenomena I mean something related to humans, organizations. They're so complex and chaotic, you can never explain 100%. In fact, if your R squared, in social sciences, if your R squared is close to 100%, then people may actually get suspicious. The reason they may be suspicious about a model that has a very high R squared is that there may be something tautological about that model. For example, in our field, which is management information systems, there is the so-called technology acceptance model or theory. This model or theory posits that technology use, which is dependent variable y, is determined by two other variables or constructs, which is technology usefulness, number one, and number two, technology ease of use. Now, some people, including myself, are arguing that this model or theory is tautological because even linguistically, right, if you say to yourself, use, usefulness, ease of use, they sound very similar, right? The reason you're using something because there's use in it, because there's usefulness, right? And also because it's easy to use, it's possible to be used. So you're saying you're using it because it's possible to be used. So the model is tautological. You're basically saying that that's almost what you're saying, that use is related to use. Now imagine if I'm a psychiatrist and I'm trying to develop a model or theory of what determines people's happiness. And so happiness is my dependent variable y. And I'm saying that happiness variable y is determined by x, which is joy, right? I'm saying that if somebody is joyful, then he or she is happy. Now, this is a tautological model because happiness and joy, they're very similar concepts. They're almost the same. So that's why you'll get a very high R squared because the model is tautological. In social sciences, such complex human-related phenomena as happiness are rarely explained in terms of one variable. So if you can explain 90% of variation in happiness based on another variable, it usually means that there's something fishy, there's something tautological in your model. Now, on the other hand, if you can predict, let's say, stock price of Apple computers, so that's your variable y, based, let's say, on last year's milk production in Wisconsin, right? If you can do that, then there's no tautology here because milk production is not related to Apple anyhow. And you can use this model for practical purposes. You can use this model to predict stock prices of Apple and make a lot of money out of that. So that would be a model that is not tautological. So what I'm trying to say is that in social sciences, your R square should be somewhere between maybe 20% and 60 or 70%. And that would be great. So anything above 20 or 30% should be great. If you have something too close to 100%, then it's a bit suspicious, to be honest. So R squared, how good your model is describing data. And then, so this is like, those are macro level indicators for your regression output. Then you will look at some micro indicators, meaning for specific estimates of A and B, which means the slope coefficient and the intercept term B. So the value of the intercept is 33.89. That's what we saw before. So that's the value. Now the question becomes, is this value valid? Okay. Again, I don't want to give you, I don't want and I cannot explain to you what statistics is in a minute or in a few seconds, but ultimately it comes down to this. Statistics is all about predicting something about the population, meaning the actual world, based on limited data, based on a smaller sample. So here we have a sample of fathers and sons, but obviously we do not have observations for all fathers and sons in the world. So based on the sample, we calculate this intercept term, but then statisticians have tools and reasoning mechanism to estimate what is the likelihood that this estimate is true for the entire population. So here, the statistic that you're looking is T statistic. The rule of thumb is that a high T statistic, something above 6, 5, 6, usually is significant. That depends on a lot of factors. It depends on the sample size and it depends on the effect size. But basically, if T is high, it's good. And then if you have p-value, which is probability associated with this estimate, that is very low, close to 0, it means that we are very confident that this is the true estimate for the population. By the way, 3 stars is good. It means that the p-value is less than 0.001, okay? Which means that the chance that, the probability that this estimate is not valid is a fluke. It's something that is derived from randomness and not from the relationship in the true population, is very small. It's almost 0. So anything that has a star is considered to be good. Now, some scientists would also accept 0.5, which is 5%. Okay, but I haven't seen people really going above 5%. So 5% means you're 95% confident that this relationship, this estimate is valid. Okay, so most scientists, they would go for much more stringent format, and they would at least require 99% confidence. And the same thing for the coefficient. This, we are talking about the slope here before x, or father's height, is 0.5. That's estimated from data. The t-value is very high, the p-value is low. So low p-value is good, high t-value is also good. Low t-value is bad and high p-value is bad, which means that we cannot prove anything based on our data, right? So those are the interpretations of the regression model, and those are the things typically scientists reflect upon when they get an output of a regression model. So I have just explained to you briefly how to interpret output of a regression model generated with the help of LM, regression approximation function, and also summary function that gives you that detailed output when you apply it to an object that contains the output of your regression model. Now, if you want to describe your data and your regression model in text, let's say as a part of a research report, then I suggest you use the so-called Stargazer R package. So this is what we will do right now. We will install this package, and we will also load it using the library command. So I'll pause for a second to get these two things done. So now the package is installed and it's also loaded. So now we are ready to use it. There's, from what I remember, the last time I checked, there's only one function that is a part of the Stargazer package, and this function is called Stargazer. So here we're applying the Stargazer function to the father-son data set, something that we loaded earlier, and the output that we're generating is HTML. So here you're creating basically a descriptives table, a table that contains a series, several descriptive statistics for each of the variables in the father-son data set, which is father height and son height in inches. So that's what we will do right now. Okay, something happened. We probably didn't load package. Let me quickly check. I think I unloaded accidentally. So yeah, I'm using it. I'm activating it here from that panel. So now it's loaded, so it should generate HTML code. So what do you do with this HTML code? Just copy it and save it into an HTML file. I'll show you like one quick way to do it. Find Notepad. So save it into Notepad, and when you save your file, name it as HTML. So let's call it tables HTML. So this is table 1, and then we'll use the Stargazer function to create a nice looking regression table that contains all the outputs that you just saw, but in a nice Microsoft Word-like fashion. So we run this command. So this is our HTML output. Again, I will just copy it from the console using Ctrl+C, and I'll append it to our HTML table here. So I'll go File, Save, and then what you can do, you can open that HTML file either in your browser, and then you can copy those tables into a Word document, or you can just simply open it using Word. So here I'll find Word really quick, and then I'll go to File, Open, and I'll just select, I'll go to Desktop, and I'll select Tables HTML. So here they are. Those are the nice looking tables that we generated using the Stargazer package. You can copy them, you can modify them further, just like as you would normally do with tables in Microsoft Word. So that completes part 1 of our video tutorial. This is our coverage of simple linear regression model in R. In other parts, we will talk about some variations, some slight variations of the simple linear regression model, and also some nuances and practical examples of linear of regression modeling and linear models in R.